Good afternoon, teacher. Today I will present my work on the enhancement of null subtraction imaging in ultrafast ultrasound beamforming. To begin, we note that conventional ultrasound relies on beam imaging, which performs a line-by-line focus scan. The received echoes are reconstructed using the delay and zoom algorithm. Thus, a simple method that aligns the signals according to their delays and then sums them up to obtain the final image. While this approach is simple and enables real-time performance, it also presents important limitations. The acquisition is relatively slow, the method struggles to suppress noise because all the received signals are given the same weight, and the resulting lateral resolution is limited. As a consequence, weak but clinically significant signals may not be properly visualized. To address these shortcomings, ultrafast ultrasound imaging was introduced. Instead of transmitting one focus bit at a time, ultrafast imaging uses plane wave imaging, where the entire array transmits a plane wave simultaneously. This produces extremely high frame rates, but at the expense of degraded resolution and contrast. To improve image quality, coherent plane wave compounding was introduced, which combines several plane waves stored at different angles to enhance the image. Although this produces better results than single-edge plane wave imaging, it still doesn't reach the resolution obtained with focused beam imaging. This motivates the exploration of more advanced beamforming strategies, including nonlinear approaches such as the null subtraction imaging. NSI reconstructs an image from three separately apologized received images, each created using different apologization pattern. Each pattern depends on a parameter known as the DC bias, which I will discuss shortly. The objective of these apologizations is to create a central null, which is then recentered by balancing the beam energy and suppressing side lobes. The first apologization generates the central null by dividing the pattern into two halves with weights +1 and -1. The second apologization uses the same zeroing pattern, but adds the DC bias. This shifts the main lobe slightly toward the positive steering direction and partially restores on-axis energy lost in the zero main configuration. The third apologization is the inverted version of the second. By combining the three resulting images using the nonlinear NSI formula, the method recenters the main lobe and suppresses the side lobes, producing an image with improved lateral resolution at a low computational cost. However, NSI depends heavily on the value of the DC bias. A small bias sharpens resolution but destroys speckle texture, while a large bias preserves speckle but reduces resolution. Since different regions of the image requires different bias values, using a single fixed bias across the entire frame leads to inconsistent results. This limitation motivates the development of adaptive, adaptive versions of NSI. The first adaptive approach is the GCF-based dynamic DC bias NCI. This method adjusts the DC bias at each pixel using the generalized coherence factor, which measures how coherent the received signals are at each imaging point. High coherence values indicate strong and well-aligned echoes, typically approaching 1. In contrast, low coherence values close to 0 are associated with noise, while intermediate values reflect the speckle-dominated regions. In this method, first, the GCF is calculated from the raw data. Then, depending on the local GCF value, the DC bias is computed so that each region receives the value that best balance resolution and speckle preservation. After the bias is determined, NC is computed in the conventional way. And finally, a normalization step is applied. In this step, the NCI output is divided by a matrix of the locally estimated bias values, ensuring that brightness remains uniform across the entire image. The performance of this method was evaluated using multiple types of data, including simulations, phantom experiments, and in vivo acquisitions, where the authors analyzed standard metrics such as the lateral resolution with the full width at half maximum, the contrast ratio, the generalized CNR, and speckle stability using the speckle signal-to-noise ratio. Comparing four methods, the GCF-based dynamic DC bias with the DAS, the GCF, and a fixed bias NCI with a DC bias of 0.05. In the simulated point target experiments, the proposed method achieved the second narrowest main loop with a full width at half maximum value of 0.08, slightly wider than the 0.07 obtained by the standard NCI, but markedly better than the 0.56 achieved by DAS and GCF. In the contrast parameters, we can see that the standard NCI has a darker image, while the proposed method has the one with better contrast. We can observe this because it obtained the highest CR contrast ratio value of 79.22, compared with the 58.43 for GCF. Also, we can see that both GCF and the dynamic bias NCI achieve high generalized CNR values of 0.99. In the case of the phantom cyst experiment, the proposed method again exhibits improved contrast between the cyst and its background. While the standard NCI performs poorly, for this case as well, the proposed method reaches the highest generalized CNR value of 0.99. And in the in vivo imaging of the carotid artery, the proposed method demonstrates clearer anatomical boundaries compared with the classical NCI, which tends to generate dark low contrast images. These results show that the dynamic DC bias approach successfully addresses the limitations of conventional NCI while maintaining low computational complexity. The second adaptive extension is the spatially smoothed adaptive NCI, or the SANSI. Instead of using queries, this method computes the bias based on the angular stability of DAS responses across different transmission angles, quantified by the signal mean to standard deviation factor. High values of this factor indicate coherent regions, while low values indicate noise. Then, the normalized factor uses this to calculate adaptive bias according to this formulation. This formulation causes pixels with high values of the factor to be assigned a small bias to prioritize resolution, while pixels with low ones receive a larger bias to preserve speckled texture. However, because pixel-wise bias estimation is extremely sensitive to local fluctuations, SANSI applies an spatial smoothing, using overlapping subapertures, producing a more stable bias map. Then the NCI is again computed in the conventional way. In the case of SANSI, the performance of the beamformer was assessed using 4 datasets: simulation resolution and contrast, experimental contrast and resolution, and finally an additional in vivo dataset. The results demonstrate that SANSI achieves competitive resolution, strong contrast, and excellent speckle preservation. In the simulation dataset, it produces the best contrast ratio with a value of 43.70 and the best generalized CN factor with 0.78. Also, we can see in the image that the standard NCI continues to generate dark resolutions. In the experimental datasets, the proposed method achieves the highest speckle SNR of 1.66, with the second smallest full width value at half maximum of 0.31. Also, we can see that SANSI maintains the speckle structure while improving contrast and resolution, unlike the baseline NCI. In vivo imaging again shows that SANSI outperforms all other tested beamformers, with the minimum full width at half maximum value and the highest contrast ratio value. Finally, I would like to include the case of high-resolution power Doppler, because it provides additional insight in how NCI improves not only structural imaging, but also vascular imaging. The method achieves significantly sharper visualization of microvessels. In a contrast and case imaging of a rat brain, for example, the full width at half maximum value decreases from 120 micrometers using DAS to only 20 micrometers using NSI. Without contrast, it decreases from 110 to 50 micrometers. These improvements enable the visualization of vessels separated by only a few tens of micrometers, something that conventional Doppler beamforming cannot achieve. Regarding clinical applications, the dynamic DC bias NCI method enhances the visualization of small anatomical structures and improves contrast in anatomically diverse regions such as the carotid artery, thyroid, and parotid gland. The NCI-based power Doppler technique is particularly promising for microvascular assessment. And the SANSI, although more computationally complex, is well suited for applications where speckle fidelity is crucial, such as soft tissue imaging, musculoskeletal evaluation, and detailed characterization of focal lesions. To conclude, the studies reviewed in this work show that while conventional NSI already improved lateral resolution, its dependence on a fixed DC bias limits its performance. Adaptive pictures of NSI, such as the dynamic DC bias and SANSI, overcome this limitation by adjusting the bias according to local acoustic characteristics. These methods consistently improve resolution, contrast, and spatial fidelity across simulations, phantom datasets, and in vivo imaging. Furthermore, the extension of NSI to microvascular power Doppler imaging highlights the versatility of this method. Overall, NSI-based strategies offer a strong balance between image quality and computational efficiency, making them promising candidates for next generation of ultrafast ultrasound systems.